let's take a look at tartaric acid, essentially the compound that Louis Pasteur was looking at. Statistically, I can do 4 combinations. There are 2 chirality centers, okay, in a molecule of tartaric acid. Carbon 2, it's a 4-carbon chain, CO2H on each end, an OH on the middle 2 carbons. So carbon 2 and 3 are chirality centers. 2R3R, and it's enantiomer 2S3S, right? 2R3S, and it's enantiomer 2S3R. So the last 2, though, right, let's look very carefully at these last 2. They're actually the same. Right? This one is the same as its mirror image. How on earth do I know that? If I keep this flat on the paper and rotate it 180 degrees in either direction. Okay? If you just spin this around, I have 2 up OHs that are pointing to the right. I spin it around flat on the paper, those 2 OHs will still be up and pointing to the left. These are the same molecule. So there are not 4 different stereoisomers of tartaric acid. There are actually 3. 2 are enantiomers of each other, and 1 is achiral. That was an original definition that we talked about. If something can be the same as its mirror image, I can hold this in the mirror and it looks the same as the molecule itself. Especially if I turn it around, I can get the same thing. These are not the case. If I turned those around, I could turn this around and it's the same as itself, but not the same as its mirror image. So these 2 structures over here, it's actually the same molecule. They're identical because there's an internal symmetry plane straight between the 2 carbons. If I've got the 2 middle carbons going up and down, for instance, if I reflect it that way, we can see pretty clearly that there's an internal symmetry plane. And whenever we have that, it's an achiral compound, even though there are chirality centers within that molecule. Because of its particular arrangement, it is achiral. So that's this definition here. This compound is called meso. A compound is meso when it is an achiral molecule which contains chirality centers. So there are actually 3 stereoisomers of tartaric acid. There is plus, its enantiomer minus, and meso, okay? Tartaric acid. If I had a pure sample of plus tartaric acid, it would rotate light clockwise. Pure sample of minus, it would rotate light counterclockwise. If I had a pure sample of meso, it would not rotate light. It's a single substance, but it's achiral, so not optically active. So let's see if we know meso. Can I find any meso compounds here? Well, 2 OHs up on carbon 1 and 2 of cyclopentane. I can pretty clearly envision a internal symmetry plane in that one. Okay, so that one is meso. There is no symmetry plane on this one. That same one that we had before is no longer a symmetry plane because where the OH is on the left, there is an H on the right, for instance, both pointed up. Not in the paper, okay, because there's an OH up and an H down, so no. What about this one? Well, I've got 5-membered ring, that's flat. I've got 2 carbons coming forward and 1 going back on the next ring. It's a quaternary center, so called a spirocyclic compound. And then a methyl group pointed up. Sometimes what it's helpful to do is draw little dots on the atoms that are in the plane of the paper. So obviously the 5 on the flat ring are in the plane of the paper. And that one's forward, that one's back, but this one is in the plane of the paper. And because we had forward and back from there, the CH3 and the H are actually in the plane of the paper. The only ones outside are these two, so I'll draw it sort of an arrow shown that way, and then that one, which is back, like that. You might have to make a model to be sure of that one. But because of that plane of the paper, I've got 2 carbons ahead of it and 1 carbon back. So no, that one is not meso. If I tried to pick it up and have a plane perpendicular to the paper, that's not meso either, because there's a methyl group on one side and an H on the other side. I could, though, make a small modification to make this a meso compound. The problem with our original plan was that there's this 5-membered ring that had 1 in front and 1 behind on there. So that was not helpful to us. If instead I made that into a 6-membered ring, and then did something like that, then that's meso. Okay? I could have 2 of these forward and 2 back, but otherwise everything else is. So that's meso, that's no. It may look like this one is not meso, but remember, this is a CC single bond, which can rotate. If I spin this around, okay, if I take this bond of 1 and turn it 60 degrees, the CH3 goes there, the H goes to the bottom, the Br goes to the left, then they become matched up, and then there's a mirror plane there, so that one is meso. So if there's a CC single bond, gotta be careful, you may have to rotate that CC single bond in order to figure out if it's meso or not. If I have 2 molecules that are enantiomers of each other, they'll have the same physical properties because they're mirror images. So they will boil the same, they'll have the same density, same solubility, all that stuff. They'll undergo similar chemical reactions and so on. They'll have all the same properties, physical properties, except direction of rotation of plane polarized light. Right? That's particular to opposite behavior in enantiomers, as well as some biological properties. In a lot of our biological senses, we have 3-dimensional, we have chiral receptors for smell, for instance, where only one certain handed version fits within the receptor, just like only one glove fits over one of our hands, right? So smell can be different in enantiomers. Toxicity, if a drug is made as a mixture of 2 enantiomers, it could be that one is the effective drug and the other is toxic. That's actually happened. You may have heard of thalidomide, a drug used in the 60s to combat morning sickness for pregnant women. Only one enantiomer was the active form. The other was actually pretty bad. It caused birth defects. So this concept of making only one enantiomer of something is really relatively new. You know, it sort of started in the 60s around the big scare around thalidomide. Incomplete understanding of chirality is what caused that. So that's enantiomers, the same in every way except direction of light and some biological properties. Diastereomers are completely different compounds. So they have the same molar mass, but that's it. They're differently shaped. They'll fit in a completely different receptor, but they'll also boil differently. You know, one could be polar, one could be non-polar, right? So if you take a look at these 3 stereoisomers of tartaric acid, like we talked about, plus and minus have the same melting point, plus and minus have the same density, plus and minus have the same solubility. They have opposite optical rotation, equal and opposite, plus 12 and minus 12. The meso compound is different from those other 2. It has a different melting point, has no optical activity, because it's achiral, different density, different solubility. Let's see if we could do that same analysis with the enantiomer of B. Right? So let's draw B again from up above on the top of the page there. I'll just redraw it here so we can see it well. So OH forward and OH back. So cyclopentane 1,2-diol. Okay? So I do trans here. 1 forward, 1 back. if I assigned configuration of these chirality centers, 1, 2, 3, and the H going back is 4 on that one, so that is R. Similar, 1, 2, 3, 4, and H going forward. It looks like S, but H is going forward, so that's actually R also. So B was RR. Let's draw its enantiomer. I could draw it as a perfect mirror image, or I could draw it as the same molecule but with opposite configurations at its chirality centers. Enantiomer of B. I just essentially picked this one up and turned it over to make that one. So when I have a molecule and its enantiomer, by definition, the stereocenters change configuration, so S and S. So I have RR and S, those are two enantiomers. Okay. The enantiomer of B will have the same properties, everything except direction of optical rotation. A was the meso compound. Both the OHs go in the same direction. I can actually do the configuration of this quickly because one of them looks like the S, one of them looks like the R from the other one. RS, if I made the mirror image, I'd get SR, but it's the same thing. Okay, meso. The meso compound would have different properties all around than all of these, and would have no direction of its polarized light. So different melting point, different boiling point, different solubility, different density. The enantiomers of A and B, they would rotate light differently from each other. They may smell or taste different, but otherwise all of their properties are identical.